This is the DPA distributor type fuel injection pump. After many years of intensive research and development, this completely new design of injection pump has been introduced by C.A.V. Limited of London to cater for the light, high-speed diesel engines now in such popular demand. These engines have already proved themselves as highly efficient, economical, and versatile power units. To mention just a few of the applications to which they're being put, they're providing the motive power for taxicabs, private cars, trucks, lorries, and a diversity of machines and appliances used in agriculture. The DPA fuel injection pump, now in large-scale production, over 400,000 were manufactured up to the end of 1960, has become standard equipment on a number of well-known engines. Apart from its inherent simplicity, there are many technical features which heighten its appeal. The advanced design lends itself to compactness. Here's a comparison of the size of the DPA pump with that of a conventional inline pump. Both are six-cylinder models with mechanical governors designed for similar duties. And here's another version, this one fitted with a hydraulic governor. It's smaller and even more compact. The hydraulic governor is of simple design and has proved highly satisfactory for general automotive applications. But where particularly close speed regulation is demanded, the mechanical governor is eminently suitable. Another important feature of the design of the DPA pump is that it enables the simplest forms of drive to be employed. The vertical drive, as seen on this engine, is a typical example. And this also has the added advantage of extremely good accessibility. Here is another example with the pump mounted horizontally. Note how simple the driving arrangements are, and how snugly the pump sits alongside the engine. The rotating parts are light, and the inertia forces small. The pump contains no ball or roller bearings, no gears or highly stressed springs. And as the casing is completely filled with filtered fuel oil under moderate pressure at all times, special lubrication is not required. Also, the pressure within the housing prevents the ingress of water and dirt. A radical departure from orthodox injection pump design is the employment of only one pumping element, irrespective of the number of engine cylinders. As is generally known, it's been standard practice for fuel injection pumps, and this is a typical example, to employ a separate pumping element for each cylinder of the engine. The element comprising a plunger and barrel with a suitable means of output control. In the DPA pump, a single pumping element supplies all the cylinders in turn with their charge of fuel. The pumping element consists of twin opposed plungers situated transversely in the central rotating member, which also acts as the distributor. This rotor revolves in a stationary member, the hydraulic head, and the pump plungers are actuated by contact with cam lobes on a stationary internal cam ring. The accurately metered high-pressure charges of fuel oil are distributed to the engine cylinders in correct firing order and at the required timing interval through a system of ports in the rotor and hydraulic head. This ghosted view of the pump shows how charging, pumping, and distribution is carried out. With the rotor in the inlet position, the rollers are off the cam lobes, and the metering port in the hydraulic head is in register with one of the charging ports of the rotor. The distributor, or outlet port, is well out of register with the discharge ports in the head. Fuel, under moderate pressure, flows in from a transfer pump through the axial passage in the rotor into the space between the plungers, forcing them apart. With the rotation of the rotor, the relative positions change. The inlet port is now closed, and the distributor port is in register with one of the fuel outlets. The cams force the plungers inwards, and the fuel is discharged under high pressure to the injectors. DPA pump is especially suited for high-speed operation. The rotating parts, being light, have little inertia. There are no return springs. The plungers of the pumping element being returned hydraulically. The present range of distributor-type pumps caters for engines of up to 2 liters capacity per cylinder. Already specified and installed in production engines operating around 4,000 RPM, even higher speeds are envisaged in the future. The C.A.V. distributor-type fuel injection pump is by far the simplest and functionally the most satisfactory pump of this type yet devised, and its introduction may well prove to be a milestone in the progress and future development of the diesel engine.
Você vai vendo aí.
The efficiency of a modern diesel engine depends to a large extent upon the correct functioning of its fuel injection system. In simple terms, the fuel, after first being filtered to remove impurities, is pumped to the cylinders in accurately metered quantities, exactly timed, and proportional to the amount of work it has to do. For maximum efficiency, it's essential that the engine should receive each charge of fuel atomized so that it can be completely consumed within the combustion chamber. This is the important function of the injectors. Here is a nozzle of a typical injector removed from its holder. This comparatively small but vital component is the key to diesel efficiency and performance, because easy starting, smooth running, maximum power, optimum fuel consumption, and freedom from smoke all depend on the correct atomization of the fuel. Injectors have to deal with hundreds of fuel charges a minute under widely varying conditions of pressure and temperature. Extreme precision and specialized techniques are called for in their manufacture, and for this reason, C.A.V. planned a completely new plant to concentrate exclusively on large-scale production of diesel injectors. At the pleasant and fast-expanding old market town of Sudbury in Suffolk, which, by the way, was the birthplace and home of Gainsborough, the 18th century painter, one of the most modern and best-equipped factories of its kind in Europe has been built. Covering some 180,000 square feet, it affords spacious and pleasant working conditions and in all respects is an ideal factory specifically designed for its job. Being purpose-built, practical advantage was taken in the planning stages of the knowledge gained over the years in this specialized field of manufacture. And this efficient and orderly layout is the result. A high degree of automation has been adopted and many special purpose machines have been developed. Before watching some of these machines in action, a closer examination of the end product will help in appreciating what is entailed in their manufacture. In the first place, there's no such thing as a standard injector or nozzle. The reason being that diesels differ considerably in regard to their injection requirements. And accordingly, C.A.V. produce a wide range to suit every requirement. These represent the main basic types of nozzle. There is the single hole, the multi-hole, and the pintle. These are available in 4 sizes and from all the variants possible. Over 100 different patterns are manufactured. Nozzles are made to the highest standards of precision. This one is cut away to show the internal construction. As pressures between the pump and injector may exceed 9,000 pounds per square inch, there must be the closest possible fit between the needle valve and its nozzle, yet allowing it to work freely. This example of extreme accuracy applies very much to injectors as a whole, and some glimpses of their manufacture will show how precision is achieved with mass production methods. Nozzles and needles start life as steel rods, and the injector bodies as forgings. Overhead cranes feed the steel to automatic machine tools where the preliminary operations take place. Here, needles are being formed. And on similar automatics, nozzles begin to take shape. Nearby, an impressive-looking machine is involved with injector bodies. This is one of many special-purpose machine tools developed for the specific requirements of injector manufacture. This one in particular carries out in consecutive sequence all the major machining, drilling, and threading operations on body forgings. And here is the finished result. At one of the many inspections that are made at all stages of manufacture, the bodies are accurately checked. Back on the nozzle line, further operations are underway. Here, the fuel chamber inside the nozzle is being formed. This is the space below the needle bore. More special-purpose machines are employed for drilling the feed and dowel holes in nozzles, one feeding to the fuel chamber, the others being locating holes for dowels in the holder body. The next operation is the exterior shaping of the nozzle. This is a blank before machining, and this is how it leaves the machine. And now comes the delicate operation of drilling the minute injection holes, another instance where special techniques are employed. This nozzle is a long stem multi-hole type, and it'll be noticed that as each hole is drilled, the machine automatically indexes the nozzle through the required compound angle. Some idea of the smallness of the drill can be gathered from this much magnified comparison with the eye of an ordinary fine sewing needle on the right of the drill, or the pin's head on the left. Up to this point of manufacture, all machining and drilling operations are carried out in what is known as the soft stage. Now follows heat treatment. Nozzles and needles undergo a hardening and tempering process in automatic furnaces. In batches, they are heated to a temperature of 1200 degrees Fahrenheit, cooled, deep frozen down to -80 Fahrenheit. This reforms the molecular structure of the metal, and then tempered by reheating to complete the 5-hour cycle. Holder bodies receive localized high-frequency heat treatment. In this process, the area coming into contact with the nozzle is hardened, which, after lapping, forms a leak-proof joint when in contact with its nozzle. The face of the nozzle is also lapped after hardening. After emerging from this heat treatment, nozzles and needles pass on to the finishing stages, where the very fine surface finishes are imparted and working fits to the closest possible tolerances are obtained. To achieve this, more special-purpose machinery has been introduced. Here, the outside diameter and the valve seat of needles are being ground to fine limits. Whilst these automatics grind the external surfaces of nozzles. Further examples of precision automation are the machines that finish the internal bore and valve seating. In a nozzle, it's imperative that the valve seating is concentric with the bore. And to ensure this, special two-spindle machines have been developed which enable both bore and seating to be ground from the same location. When measured, the walls of the finished bore must be parallel to within 2 microns, a micron being 1/25,000th of an inch. This is the degree of accuracy that these machines are capable of achieving, as rigid inspection proves. This is one of the important checking points that every nozzle passes when completed. All the critical dimensions are accurately measured and the bore and valve seating closely inspected. Now comes the moment when nozzles and needles come together for the first time. The tolerance between the two components is already to very close limits, but to ensure the most perfect fit, a minute fraction is ground from the needle. The amount to be removed, although infinitesimal, is exactly determined as each nozzle is gauged, this automatically giving the correct setting to the machine. Once needles and nozzles are mated, the parts are never interchanged. This film has dealt briefly with some of the highlights of injector manufacture and the modern techniques that are employed to ensure the highest standards of quality and precision. There are many other aspects of C.A.V. at Sudbury that support these aims, and they would make a complete story in themselves. For instance, they have one of the world's most advanced electronic telecontrol systems for loading and monitoring every operation in the factory. And there's a fully equipped laboratory that keeps a constant check on both raw materials and finished product. These all play their part in the assurance of quality in this critical component. Quality that is enclosed in a special hermetically sealed inner pack as a final protection in storage. For maximum diesel performance, keep an eye on the injectors. And remember, the right nozzle for the C.A.V. injector is the C.A.V. nozzle.
Over the years, the diesel, or more correctly the compression ignition engine, has firmly established itself as a highly efficient, economical and versatile power unit. More recently, there's been a growing need for smaller, lighter diesel engines, capable of higher operating speeds, yet still retaining all the advantages that the larger diesel affords. Engine manufacturers have been carrying out intensive development work with the object of meeting this requirement. And as a result, more and more of these small engines are making their appearance. The underlying factor that had to be considered in the early stage of development of these engines was one of cost. It was clear that in the small engine field, the fuel injection equipment naturally tended to represent a larger proportion of the total engine cost than it did on the bigger types of engine. The relatively high cost of this equipment is understandable when one appreciates the vital part that this equipment has to play and the high precision called for in its manufacture. From the outset, the need for cost reductions was fully apparent, and C.A.V. Limited, as leading manufacturers of fuel injection equipment, put in hand a program of research with this object in view. A completely fresh approach was made to injection pump design, and a vast amount of development and exploratory work was carried out with a number of pumps of the single-element distributor type. Some of these pumps gave quite good performances, but were considered too complex in design to enable the desired price advantage to be realized. This example is one of the later C.A.V. designs. Much exhaustive testing, both in the laboratory and in the field, led finally to the adoption and introduction of the DPA distributor type fuel injection pump, a highly efficient unit fully capable of meeting the requirements of the lighter high-speed engines. This pump has now been in large-scale production for some time and has become standard equipment on a number of well-known engines. In addition to the advantage the distributor type of pump has to offer in regard to cost, there are many technical features which considerably heighten its appeal. Apart from its inherent simplicity, the design lends itself to compactness. Here is a comparison of the size of the DPA pump with that of a conventional inline pump. Both are 6-cylinder vehicles with mechanical governors designed for similar duties. And here is another version of the DPA pump, this one with a hydraulic governor, which is smaller and even more compact. A most important factor from the cost reduction viewpoint is that the design of the DPA pump lends itself to the simplest and least expensive forms of drive. Thus, there can be considerable simplification of the driving arrangements on the engine, which result in worthwhile savings. The simple vertical distributor type drive, as seen on this engine, is one of the best examples. And this also gives the added advantage of specially good accessibility. Here is another example with the pump horizontal. Note how simple the driving arrangements are, and how snugly the pump sits alongside the engine. The rotating parts are light, and the inertia forces small. The pump contains no ball or roller bearings, no gears or highly stressed springs, and the casing is completely filled with fuel oil under moderate pressure. Special lubrication is therefore not required, and the pressure within the housing prevents the ingress of water, oil, and dirt. A radical departure from orthodox injection pump design is the employment of only one pumping element, irrespective of the number of engine cylinders. As is generally known, it has been standard practice for fuel injection pumps, and this is a typical example, to be provided with a separate pumping element for each cylinder, the element comprising a plunger and barrel with a suitable means of output control. In the DPA pump, the single pumping element supplies all the cylinders in turn with their charge of fuel, with a distributor connecting the pump delivery to the individual injectors. The method of distribution is in some ways similar to that employed to distribute the spark in the ignition system of a petrol engine. Of course, the diesel engine has no sparking plugs, but with the DPA pump, the fuel oil is distributed to each injector in turn from the single pumping element. Here are some of the principal parts of the DPA pump. This is the hydraulic head, with its central rotating member, the pumping and distributing rotor. The rotor and head are machined to extremely fine limits and form a mated assembly. At one end of the rotor is the pumping section, where two opposed plungers work in a transverse bore. The plungers are actuated by cam rollers, which, as the rotor revolves, come into contact with a stationary cam ring carried in the housing. There is a central bore through the rotor which leads from the pumping chamber and connects with inlet and delivery ports. Here, in a sectional diagram, is the end-on view of the internal cam ring, in this case with 4 lobes as used for a 4-cylinder engine. And here, the rotor carrying the twin opposed plungers and cam rollers. In this, the inlet position, the rollers are off the cam lobes, allowing the plungers to move outwards as fuel enters. As the rotor revolves, the plungers are forced inwards by the cams, and the pumping action takes place. The fuel between the plungers being expelled under high pressure via the central passage and ports of the distributor. Not being spring-loaded, the plungers move outwards by fuel pressure alone. This transparent model shows how the distribution is carried out. Through the center of the rotor is the axial passage, connecting the pumping space between the plungers with a series of ports drilled radially in the rotor. The single radial hole is the distributing port, which, as the rotor turns, aligns successively with a number of equally spaced outlet ports in the hydraulic head from which the injectors are fed. There is an outlet port for each engine cylinder. Only one is shown in this model. A similar number of inlet ports are spaced round the rotor. These are lined successively with a single port in the head, the inlet or metering port. The function of metering will be dealt with later. This ghosted view shows the complete cycle of charging, pumping, and distribution. With the rotor in the inlet position, the rollers are off the cam lobes, and the metering port in the hydraulic head is in register with one of the charging ports of the rotor. The distributor or outlet port is well out of register with the discharge ports in the head. Fuel, under moderate pressure, flows in from a transfer pump through the axial passage in the rotor into the space between the plungers, forcing them apart. With the rotation of the rotor, the relative positions change. The inlet port is now closed, and the distributor port is in register with one of the fuel outlets. The cans force the plungers inwards, and the fuel is discharged under high pressure to the injectors. And so the cycle continues. In practice, fuel entering the pump flows first through the transfer pump, which raises the pressure to an intermediate level. The transfer pump is mounted at the upper end of the rotor. Of the positive type, it has two vanes sliding inside a liner mounted in the head, the capacity being considerably in excess of the requirements of the injection pump itself. Transfer pressure is at all times related to engine speed. An increase in speed produces an increase in transfer pressure, and similarly, a drop in speed results in the pressure falling. The pressure is controlled by a regulating valve which bypasses fuel back to the suction side of the transfer pump. This valve also provides a means of bypassing the transfer pump when hand priming is necessary. Fuel entering the pump passes first through a gauze filter into the transfer pump, flows along a passage in the hydraulic head, around an annular groove surrounding the rotor, to the metering valve. This metering valve determines the exact amount of fuel entering the pumping element and therefore the engine speed. Before explaining its operation, let us first see how the metering valve is controlled by governor action. The DPA pump is available with two alternative types of governor. The hydraulic, generally suitable for most automotive applications, and the mechanical, recommended where particularly close speed regulation is demanded. The hydraulic governor is of simple design, being operated by fuel at transfer pressure. From the annular groove surrounding the pump rotor, the fuel passes through the metering valve to an annular space round the valve. The operation of the metering valve can be followed more closely on this cutaway model. From the groove around the rotor, fuel at transfer pressure passes through the valve, which is hollow, via transverse holes to the annular space. Endwise movement of the valve varies the area of the metering port registering with the annulus. In this position, the metering valve is fully open. And here, completely closed. As the valve opens, fuel passes through the metering port, thence to the inlet ports of the rotor. This drawing shows more constructional details of the hydraulic governor and metering valve. This actuating rack, the movement of which is effected by the manual or throttle control, is free to slide on the valve stem and is held between two springs acting in opposition. The main spring and the idling spring. The loading on the main spring varies according to the position of the manual control. As the control is operated to give increased speed, the valve is pushed towards the full open position by the governor spring. As the speed of the engine increases, transfer pressure also builds up, the increased pressure forcing the valve back against the main spring until a balance is reached. When speed fluctuations occur, as the result of changes in engine loading, the governor provides an immediate and compensating change in fueling in order to maintain the selected speed. When the engine control is moved towards the idling position, the compression of the mainspring becomes progressively less, and the idling spring is compressed, enabling the reduced transfer pressure to operate the metering valve and perform the governing function throughout the idling range. A simple shut-off mechanism is also incorporated in the governor housing. A lever is provided for lifting the metering valve to the closed position, thus cutting off the fuel, stopping the engine. This is the DPA pump fitted with a mechanical governor. Although performing a similar function, the mechanical governor differs from the hydraulic type in both construction and principle of operation. In this version, the pump is somewhat longer, the housing being lengthened to accommodate the governor unit carried on the drive shaft. The main features of the pumping unit remain the same, with the exception of the metering valve, which in this instance is of the semi-rotary type. In this model, it will be seen that the valve has a groove cut along one side, which registers with the metering port as the valve rotates. The rotation progressively controls the orifice to admit more or less fuel to the pumping element. Here, the valve is moving to the fully open position. And now, completely closed. And once again, in end-on view. Valve closed, and now opened. The governor itself is of the flyweight type, the weight assembly rotating with the drive shaft. As the weights move inwards or outwards, under varying centrifugal force according to the pump speed, they operate a thrust sleeve which slides on the drive shaft. This endwise movement of the sleeve operates the control arm. This, in turn, actuates the metering valve. For simplicity, only the main parts are represented on this model. Movement of the throttle lever adjusts the load on the governor control spring, bringing about a change in the position of the control arm, and hence of the metering valve, admitting more or less fuel to the pump as required. Tensioning of the governor spring provides increased resistance to the influence of the governor weights, so that with greater tension, resulting from increased throttle opening, governor control will be at higher RPM. For any setting, the governor will maintain the speed within close limits. Within the idling speed range, tension is removed from the main governor spring, and a light idling spring gives sensitive control at low revolutions. There is a simple shut-off device incorporated in the mechanical governor. As movement of the governor control lever is transmitted to the metering valve through the medium of a lightly loaded spring link, operation of the shut-off lever can therefore override the governor control no matter in what position the weights may be, and turn the metering valve to the no fuel position. The design of the pump lends itself to the application of a simple automatic advance control mechanism. This hydraulically operated device provides a means of advancing the injection timing progressively as engine speed increases. The transfer pressure, rising with increase in speed, operates a servo piston against spring pressures, advancing the cam ring as required, to give a predetermined timing curve. Here, in model form, we see the cam ring in the fully retarded position. As transfer pressure builds up, with an increase in engine speed, the piston moves along the cylinder to rotate the cam ring to the fully advanced position. When the engine speed falls, transfer pressure decreases, and the piston and cam ring are moved towards the retarded position by spring pressure. The addition of automatic injection advance is of particular value in achieving optimum performance over a wide speed range, and can also assist cold starting. It will be seen that the cam lobes do not follow a continuous lift and fall contour, but provide for a suitable retraction period at the termination of injection. This has the effect of unloading the fuel lines and prevents dribbling at the nozzles. Calibration and phasing, operations necessary in adjusting an inline pump, are unnecessary with the DPA pump, since they are provided for by the accurate spacing of the ports in the rotor and head during manufacture. The only adjustment provided on the DPA pump is that for maximum fuel setting. The maximum amount of fuel entering the pumping element is controlled by limiting the outward movement of the plungers. Adjusting plates, located on the pumping section of the rotor, enable the correct setting to be made. It will be seen that the limiting slots in the plate, in which the projecting lugs of the roller shoes are inserted, are eccentric, and the outward travel of the cam rollers, and with them the plungers, is reduced or increased according to the setting. This large-scale model shows how this adjustment operates by controlling the maximum effective pumping stroke of the plungers. The correct setting is made when the pump is tested after manufacture, and should not be altered without approval. The DPA pump is especially suited for high-speed operation. The rotating parts, being light, have little inertia. There are no return springs, the plungers being returned hydraulically. The driving torque is always in the one direction, and there is therefore little torsional oscillation to affect the drive. The pump is lubricated throughout by filtered fuel oil, the housing being maintained completely filled during operation by back leakage of oil through a groove machined on the rotor. The present range of distributor-type pumps caters for engines of up to 2 liters capacity per cylinder. Already specified and installed in production engines operating around 4,000 RPM, even higher speeds are envisaged in the future, without any foreseeable difficulty. To sum up, the C.A.V. distributor-type fuel injection pump is by far the simplest and functionally the most satisfactory pump of this type yet devised. And its introduction may well prove to be a milestone in the progress and future development of the diesel engine.